Well, we're almost done. So I just want to talk to you about a few special kinds of matrices, and we'll be done for now. So first of all, if we have a square matrix, all right, again over a commutative ring, let's say, then A is symmetric if A transpose is once more equal to A. It's anti-symmetric if A transpose is equal to minus A. All right. So these are, very special kinds of matrices, and they have very, very nice properties, as we'll see. But just to give you some examples, so like a symmetric matrix might be it's 1, 2, 3. Put a 2 over here, that would be symmetric. In contrast, if I had 1, 2, 3, and I put minus 2 here, it would still not be, that would not be anti-symmetric. In fact, this would be neither symmetric nor anti-symmetric, all right? However, I could rewrite this as, for example, I could write it as 1, 0, 0, 3, plus 0, 2, minus 2, 3. And then this, in fact, well, this is a symmetric matrix. This is a special kind of symmetric matrix. This is an example of what's called a diagonal matrix. A diagonal matrix is also symmetric, but not every symmetric matrix is diagonal. For example, this is not diagonal. Can you have some gum? Well, I don't know. Spicy gum. I think I left my spicy gum at school, Isaac. I'm sorry, man. Oops. There's not supposed to be 3 there. 0. This is anti-symmetric. Now, it turns out any matrix, square matrix, can be written as a sum of a symmetric and anti-symmetric matrix, so this is like no accident that this happened. And there's a few other interesting propositions about symmetric matrices that I can give you. For example, if I look at any matrix, doesn't even have to be square. If we look at A times A transpose, first of all, that product is defined, right? Because if this is m by n, this is in fact n by m, right? Then you can prove that this is symmetric. Is a symmetric matrix. Let's see why that is. Not that hard to prove, since we already have all the necessary tools. The proof. And by the way, as we get further into this, you notice I do less and less with components. So sometimes we need components for proofs, right? But as we build more technology here with matrix algebra, we need less and less of that, which is kind of neat. A transpose transpose times A transpose by sock shoes. But of course the transpose is a thing again, so there we have A transpose. Oh, check it out. So therefore this matrix, A transpose, is equal to its own transpose. So therefore A transpose is symmetric. And there you have it. That wasn't bad, was it? You're like, please make that a test question. Yeah, no, right. And then we can do an induction to prove, by the way, there's another thing. Well, here, I'll do a simple case of it. A squared is symmetric. If we're given, now this is a horrible way to write this theorem. If we're given A is equal to A transpose, in other words, if it's symmetric, then its square is also symmetric. So let's see, assume A is equal to A transpose, or other way around, A transpose equals to A. Then consider A squared, the transpose. Well, what is that? That's A transpose, right? But then by sock shoes, that's A transpose. Although this time it's like socks. And but A is symmetric, so that's A times A. But hey, that's A squared. So there you have it. If the matrix is symmetric, then its square is symmetric. But you can prove that extends. You can prove inductively that the same is true for the kth power. And I'll let you read that. It's on page 42. I'm not going to... Well, fine, I'll go through it. Why not? Proof. So let's say, assume that A transpose is equal to A, right? So observe that A to the 1 transpose is equal to A transpose, which is equal to A. Hence, A to the K transpose is equal to A to the K for the base case of K equals to 1. All right, so suppose inductively that A to the K transpose is equal to A to the K for some K in the natural numbers. Consider, that was supposed to be consider, no, we've got extra in there, A to the K plus 1 transpose, right? So what is that? Well, that is A to the K times A transpose, which by sock shoes is A transpose, A to the K transpose, right? Sock shoes, which you're going to prove in your homework. And then, okay, we're assuming A is symmetric, so that's A. And by the induction hypothesis, that is A to the K. So that's, again, by A transpose equals to A was assumed, and the induction hypothesis. All right? And so, hey, well, that's A to the K plus 1, and there you have it. So, thus, A to the K plus 1 transpose equal to A to K plus 1. And that shows you, of course, that A to the K plus 1 is symmetric, and that shows you that the induction claim for order K implies K plus 1 is true, and hence, by proof by mathematical induction, if a matrix is symmetric, any natural number power of the matrix is also symmetric. All right. So, yeah. That's a nice little induction argument. And then finally, I just have a word or two about diagonal matrices. So, like, diagonal matrix looks like this. This is upper triangular matrix, something like that. This is a lower triangular matrix, something like that. Any matrix can be written as a sum of a lower triangular, a diagonal, and a diagonal, lower triangular, and strictly upper triangular, right? Because you can always kind of just break it up into above and below and the diagonal itself. And you can also prove that diagonal and triangular, it's like the product of diagonal matrices is diagonal. The product of lower triangular matrices is once more lower triangular. The product of upper triangular matrices is once more upper triangular. We say strictly if we want to exclude diagonals, but anyway, this is not an accident. The fact that it happens for the 2x2 case means that's not a proof, but in fact it is true that this continues to be the case for n by n matrices. It always, the product of triangular matrices is once more triangular, either upper or lower. All right, so I'll let you. Now the proof of that uses pretty, fairly involved index calculation, but it's, it's not impossible to understand. Now finally, I just want to say a word or two about nilpotent matrices. So definition, and we'll come back to these triangular and diagonal matrices as we go on in this course. I'm just introducing the terminology briefly, and I'll probably give you some kind of homework on it. So suppose you get a square matrix n, and n to the k is equal to 0, but n to the j is not equal to 0 for j equals to 1, 2, all the way up to k minus 1. In other words, the k is the first positive integer for which the matrix, the kth power of the matrix is 0. We say n is nilpotent of degree k. Sometimes I say of order k. All right. Now these are interesting matrices, obviously. Kind of weird. You got something non-zero, and you raise it to a power, it becomes 0. That's a little bit unnerving, right? So for 2x2 matrix, nilpotent, standard example would be like this. So if I take this times this, I get 0, and 0. Okay, so if this is n, we have n to the first power not equal to 0, obviously, but n squared is equal to 0, so n is nilpotent, order 2. I'm sorry, degree 2. Another example might be something like 0, 1, 1, 0, 0, 0, 0, 0. Right? If you look at that, and you look at, okay, so I'm saying this is my second example, n. What we get is 0, 0, 0, 0, 0, 0, 1, 0, 0. Okay, not 0 yet, right? And then if you multiply n times n times n, you get 0, 0, 1, 0, 0, 0, 0, 0, 0 times 0, 1, 0, 0, 0, 1, 0, 0, 0, which is 0. Okay. So in other words, we have n squared not equal to 0, but n cubed equal to 0. N has it's nilpotent of order 3. Nilpotent matrices are kind of interesting because if you take an identity matrix and you just like add a nilpotent matrix to it, it'll still be invertible. Here's a standard neat little example I give of that. So like if I take I plus n, that's going to be invertible because if I take this, and suppose n is degree 2, okay, suppose n squared is equal to 0. So it's like this one. So I times n, if I multiply that by I minus n, what I get is I get I plus n minus n, because ni is n, and minus n times I is minus n, and then minus n squared. But n squared being 0 goes away, and you get I again. So by uniqueness, right, I have I plus n inverse is just equal to I minus n. And some similar trick will work for nilpotent matrices of order k. You might try to see if you can figure out how to construct, oh, I'm sorry, I was writing off the page. You might see how you can do the same for like n cubed equal to 0. That's a nice little exercise. I think you need 3 terms. It involves n and n squared. But that's about it for now. Next time we'll pick up with row reduction. Thanks, guys.